right, thank you for being here towards the end of the conference. This is a joint work with Alireza Rezaei, who was very recently at UW. Now he's in the industry. So the problem we are studying is a very classical problem, approximating the permanent, which you can think of as counting the number of perfect matchings in a bipartite graph. Okay? So we have a non-negative matrix, n by n matrix. You can translate it as into a bipartite graph where the entries tell you where the edges are, and if they are weighted, then you get a weighted graph. And the permanent of this matrix is exactly the number of perfect matchings. In the case where it's weighted, you just multiply the weights for each matching. Okay? So for example, you just sum over all permuted diagonals, you multiply the entries, you sum this over, and you get the permanent. Okay? So even for 0-1 matrices, this is a sharp p-hard problem, so we are not talking about exact computation. The natural thing we are asking is approximate solutions to this. Okay? So let me tell you a somewhat incomplete history of what we know about approximations of this problem. So perhaps the first non-trivial approximation was designed by Barvinuk, who basically who designed a randomized estimator, an unbiased estimator of the permanent by designing a random matrix with random signed entries, and taking the determinant squared of that matrix would give you an estimator for the permanent. So he showed that, by bounding the variance, that this estimator with high probability gives you a constant to the n approximation. Okay? So just 1 year later, Lineal, Samarnitsky, and Wittgenstein got a deterministic algorithm that achieved a constant to the n approximation. And they did this by matrix scaling. I'll tell you what matrix scaling is later on. Okay? So in 2001, Jerome Sinclair and Vigoda basically solved the problem when you're dealing with randomized algorithms. They designed the Markov chain Monte Carlo method that gives you a 1 plus epsilon approximation in polynomial time. But still, there was this question of what can you do with deterministic algorithms, and this is still somewhat of an open question. So for a very long time, this algorithm of Lineal, Samarnitsky, and Wittgenstein, which is very simple, we'll get to it later, was the best known until in 2014, Gurvitz and Samarnitsky showed a much better approximation factor, an improved approximation factor. It's still exponential, but with a much better constant in the base of the exponent. And this approximation came from some heuristic known in the statistical physics literature as the Bethe approximation. Okay? So if you carefully look at all of the approximation factors I showed you on the previous slide, they're all either exponential or 1 plus epsilon, and there is a reason for this. As soon as you go slightly below exponential approximation, you automatically get a 1 plus epsilon approximation. Okay? So this is a well-known trick. So this makes the real question you should be asking is what is the minimum base of the exponent that you can get? Okay? So that's the natural question to ask using deterministic algorithms. Okay? So previously, we knew that alpha was less than e. It got improved to alpha is less than 2. And now we show that alpha is at most square root 2. Okay? So let me be very clear on this. We actually don't design a new algorithm. We just improve the analysis on the algorithm designed, or the Bethe approximation that was already analyzed by Gurvitz and Samarnitsky. So same algorithm as before, we just improve the analysis. So this approximation of square root 2 to the n was already conjectured by Gurvitz to be the right approximation. We just proved that conjecture. Okay? So in the next remaining part of the talk, I just want to tell you first what is the Bethe approximation, and also give you some details on how we prove the bound between Bethe approximation and the permanent. Okay? So to do this, first let me start by the earlier algorithm of Lineal, Samarnitsky, and Wittgenstein, which was by matrix scaling. So assume you want to approximate the permanent of this matrix. If I multiply the rows or columns of this matrix by some number, the same multiplication happens to the permanent. Okay? So one thing you can do is you can divide the rows by the row sums to make the row sums 1. So if you do this, the permanent basically gets reduced by the product of the row scalings that you're doing. Okay? So you get a new matrix whose row sums are 1. Now you do the same thing with the columns. The column sums might not be 1. But you exactly record what is happening to the permanent on the bottom. If you keep doing this, you converge to a matrix whose row sums and column sums are always 1. So you converge to a doubly stochastic matrix. And if you just multiply all of the scalars that you've written along the way and you multiply them, you get that the permanent of the original matrix is this factor times the permanent of this new doubly stochastic matrix. Okay? So they basically reduce the problem to computing the permanent of a doubly stochastic matrix. Now, if you're like me and you don't like iterative algorithms like this, you can also get this doubly stochastic matrix as the solution to a convex program. Okay? So there is a max entropy program. If you take the log of this becomes some sort of a relative entropy, where you're maximizing over all possible doubly stochastic matrices of this expression. Okay? The solution to this is exactly the thing you get by matrix scaling. And it's, if you look at this objective for a minute, you'll realize that after you take a log of this becomes a concave function. So you can also get this without matrix scaling in an iterative fashion by just solving this concave program. All right, so just to be clear, the solution to this concave program for this matrix that we started with is exactly this factor that we get. Okay? Now, Lineal, Samorodnitsky, and Wittgenstein use the fact that the permanent of doubly stochastic matrices is we have very good bounds on it. It's upper bounded by 1, and due to the famous van der Waals conjecture, it's always lower bounded by e to the minus n. So they said, OK, why don't I just output this number as my approximation to the permanent? So it's an upper approximation, and it's an e to the n approximation. Okay? All right, so this is synchronous scaling. Now, what is Bethe approximation? Bethe approximation is a simple modification to the objective of synchronous scaling. Okay? So I'm just multiplying some terms that only come from the doubly stochastic matrix that I'm optimizing over, and I'll tell you what the meaning of these are. But first, just notice that when I multiply these things, these are log convex, not log concave. Okay? So it's no longer trivial that you can even compute the maximization on the right-hand side. Even though it's non-trivial, it is true, and it was shown by Van Tobel in 2012. Okay? So this thing is concave over the polytope of doubly stochastic matrices. Gurwitz used an inequality due to Shriver to show that the objective on the right-hand side, which is smaller than the one on the left-hand side, is actually a lower bound on the permanent. So you get a sandwiching of the permanent between the two objectives. And the term that I've highlighted can be at most e to the n for any doubly stochastic matrix. So this is another proof that synchronous scaling gives you an e to the n approximation. Okay? But what we show is that you don't have to upper bound by synchron. You can just upper bound by a multiple of Bethe. And you get a much tighter factor than e to the n. You get square root 2 to the n. Okay? Where is this square root 2 to the n coming from? So when you first study this problem, you might go to the usual suspects. So in the case of synchron scaling, the usual suspects would be the identity matrix and the all ones matrix. In the case of the identity matrix, the permanent is 1. Synchron scaling gives you 1. Bethe approximation also gives you 1. In the case of the all ones matrix, permanent is n factorial. Synchron scaling is the maximum possible way off from the actual permanent. It's n to the n, which is off by roughly e to the n. But surprisingly, Bethe compensates for this difference. Bethe is actually a very good approximation to the permanent of this matrix. So the usual matrices aren't the ones that you should be looking at. Well, it turns out that, OK, so even though Bethe is off by only a polynomial factor, if you start with a small matrix where Bethe has some error, you can amplify that error by taking a block diagonal matrix. Okay? So for the 2 by 2 all ones matrix, Bethe is off by a constant factor 2. And if you just form a block diagonal matrix of all 2 by 2 blocks of all ones, you just amplify the gap by 2 to the number of blocks, which is square root 2 to the n. Okay? So that's where square root 2 to the n is coming from. And the reason that this conjecture, that this is the worst possible you can get was open for a while, is that in the case of Sinkhorn scaling, there is a unique matrix which is the bad example. Whereas here, you can just permute the rows and columns, and you get a bunch of bad examples. And you have to somehow, this tells you that convexity arguments, for example, don't work. You have to somehow break the symmetry between these bad examples. Okay. All right, so now let me tell you where Bethe approximation is coming from. So if you start with a matrix, or alternatively a bipartite graph representing it, both Sinkhorn scaling and Bethe approximation find a doubly stochastic matrix, which you can think of as a weighted bipartite matrix, which has degrees all equal to 1. And Sinkhorn and Bethe don't necessarily arrive at the same doubly stochastic matrix. They might arrive at different ones, but both of them find this, and in terms of that, they bound the permanent. Okay. Now so both of these methods work by solving a convex program. This is computationally efficient. There is a much more natural way of arriving at a doubly stochastic matrix, which is not computationally efficient. And that is to first go from this bipartite graph to a distribution on perfect matchings, where you just sample a random perfect matching with probability proportional to its contribution to the permanent. And then you look at the marginals of this distribution. Okay, so you just overlap all of these perfect matchings on top of each other. You do, again, get a doubly stochastic matrix, and this is different from the ones that Bethe and Sinkhorn arrive at. Okay? This is actually sharply hard to get exactly. Right? So, all right. So why is this? So why is this viewpoint useful? Well, from variational principles, you can write the permanent, which is the quantity you want, as some sort of a relative entropy between distributions you can get on perfect matchings, and this quantity, the weight of every perfect matching in your graph. Okay? So the distribution on perfect matchings that maximizes this is the distribution you get in the middle by just normalizing the weights to sum up to 1. And the output of this relative entropy program is exactly the permanent. It's the normalizing factor. Okay? Now, so this is a concave program, but on the set of distributions on perfect matchings, it's exponentially large. We don't hope to solve it. Bethe basically says, look at the doubly stochastic matrix you get at the end. This is a much smaller object. Can I reconstruct the distribution on perfect matchings from this marginal vector? And then just plug in the distribution I reconstructed from the marginals into this equation and solve the relative entropy program. Okay? So this is what Bethe does. So if you take log of this, this becomes relative entropy. I'm just not taking logs. All right. Okay. So the question is, if you know that your distribution is coming from a matrix and you know the marginals of this distribution, can you reconstruct the distribution on the perfect matchings? If I tell you this doubly stochastic matrix you get at the end, can you get the distribution on perfect matchings? And the answer is always yes. There is a unique distribution that you can get with those marginals. But this fact alone is not helping us. What we want is actually a distribution on perfect matchings that is easy to calculate with. Okay? So Bethe said, on graphs that look like trees, this distribution has actually a very simple form. The probability for every matching is exactly the product of the marginals of edges in the matching divided by the complement of marginals for edges not in the matching. Okay? So I put quotes around the trees because you'll see in a second. Okay? Now this is a true statement for trees, but not true for general graphs. But nevertheless, Bethe heuristic says, assume that even for general graphs, the formula holds. The probability of every perfect matching is exactly given by this. Then the relative entropy statement I had on the previous slide becomes the max entropy, the concave program that computes the Bethe approximation. Okay. Now, okay, so let me tell you what I mean by trees. So if your graph is a tree, the set of perfect matchings on it is not very interesting. There can be at most one. Okay? So to make it a little bit more interesting, let's work with some slightly more generalized graphs. So I assume that I have half edges in my graph as well. Okay? So these half edges are connected to one node, and the other endpoint doesn't go anywhere. And again, a perfect matching is some set of edges that has, for which every node has one adjacent edge. So for example, this is a perfect matching now. Okay? Now, let's say I want to compute the probability of this perfect matching in my distribution. Okay? I do a sweep over my graph from the left to the right, and I compute this probability step by step by computing conditional probabilities. Okay? So for example, what is the probability that E4 is in my perfect matching? It's just the marginal of the edge E4. Okay? Now, given that E4 is in my perfect matching, what is the probability that E3 is not in my matching? The conditional probability is just 1. Okay? Now, given that E3 is not in my perfect matching, what's the probability that E1 is in my perfect matching? It's just the probability of E1 divided by the probability of E1 plus probability of E2. Okay? I had two choices, E1 or E2. I just divide that. Now, the thing on the denominator is just 1 minus the probability of E3. So that's where this division by the complement of the marginals comes in. Okay? So if you just follow this, you get exactly the formula that I got, except for the half edges you don't divide. Okay? All right. So what Bethe does is it says, look, I start with a doubly stochastic matrix. I construct something that is a pseudo distribution. If my graph was a tree, this would be an actual distribution, but this is no longer a distribution. This is a pseudo distribution. It doesn't sum to 1. But nevertheless, I compute the same relative entropy with respect to this pseudo distribution, and that's my answer. Okay? All right. So now I want to tell you how do we actually upper bound the permanent, and how do we relate it to the Bethe approximation. Okay? So one of the most famous upper bounds on the permanent is due to Bregman and Mink, who showed that if you have a 0-1 matrix and you know the row sums, you can get an upper bound that looks like this. Not important for this talk what this is. But what is important is Shriver's proof for this upper bound. Okay? So Shriver basically constructed this proof method that follows along this line. You construct two distributions on the set of perfect matchings. One distribution nu I'll tell you later. The other distribution is the normal distribution, where you just take a perfect matching with probability proportional to its contribution to the permanent. Okay? Now, from the fact that the KL divergence between these two distributions has to always be positive, you automatically get an upper bound on the permanent. Okay? If you just move things around, this is an upper bound that you get on the log of the permanent. Okay? So if you notice, there are some terms which look familiar in both the Bethe approximation and in the Sinkhorn approximation. Okay? So these Pij log of Mij's, they appear in both of those approximations. Okay? So the real question is how do we design the distribution nu so that we can compare it to the rest of the terms in those approximations? So what Shriver did was he constructed the distribution in a sequential way. So he said, OK, look, I have a bipartite graph. I want to sample a perfect matching from it. I order the vertices on one side in some arbitrary order. I go over each vertex, and I pick one free neighbor for it uniformly at random or proportional to the weights. Okay? So for example, if you're choosing a neighbor for V1, maybe you choose this one out of the 3 uniformly at random. Now, both V1 and its neighbor can no longer be matched. I go over to V2. From its neighbors, I choose one uniformly at random. Maybe I pick this one, and I go over V3. That's the perfect matching I got. Okay? So nu is the distribution you get using this. Okay? So using basically what Shriver did was he constructed two distributions from the given matrix. One was mu. Another distribution of perfect matchings was this nu. And he related the KL divergence between these two to the upper bound that would prove Bregman-Mink. Okay? So our main insight is we shouldn't actually start from the matrix here. We should flip this picture. We should construct a new distribution from this doubly stochastic matrix. Okay? So what do I mean by that? you again go sequentially over vertices, but when you're choosing a neighbor for each vertex, you pick it with probability proportional to this doubly stochastic matrix, not the original matrix. Okay? So, so since I'm running out of time, let me go very quickly over this. So if you see what are the probabilities of nu according to this distribution, you get a lot of useful things. You get a lot of terms that appear in the Bethe approximation, but there is still a lot of calculation involved in relating that to the Bethe approximation. So let me just conclude. So what we get is a square root 2 to the n approximation for the permanent. The upper bound method I showed you is actually somewhat general. You don't have to just apply it to the Bethe approximation. For example, there is this thing called the fractional Bethe approximation that Chertkov and Yedida studied for the permanent, where you just take the square root of the extra terms in the Bethe approximation. Okay? So using our upper bound method, we can show that this is always an upper bound on the permanent. Sometimes this might be better than the square root 2 to the n. Okay? Now, some open questions. If you look at the bad example for Bethe approximation, the graph consisted of a bunch of cycles of length 4. There were these 2 by 2 matrices. Each one of them was a cycle of length 4. Okay? So this is, in some sense, the most far off you can be from being tree-like, having a bunch of small cycles, right? Now, the question is, can you somehow correct for these small deviations from being tree-like? So there is a candidate for doing these things. There is this hierarchy of approximations. Bethe is one of them, called the Kikuchi hierarchy. We'll hear about it in the next talk. But the question is, can we do anything to get better approximations using the Kikuchi hierarchy? Okay? There is another orthogonal direction, which is for Bethe approximation, which we know is computationally efficient. Can we prove better bounds for special classes of matrices or graphs? Okay? So one natural conjecture would be, a graph becomes more and more tree-like as the girth grows. So what happens to large girth graphs, for example, or what happens to random graphs? So in some related work, ongoing work, we've shown that for low non-negative rank matrices, we get much better than exponential approximation. But yeah, thank you.